Hi everyone. Today we will talk about the lecture. The lecture is chapter 2. The topic is overview and introduction to finite element method 2. In this lecture we will talk about the following subtopic. The subtopic is finite element method. We will introduce the detail for the concept of this method. Another one is the element characteristic matrix. We will show you how to create the element characteristic matrix. And then we will introduce the element assembly and the solution for unknown. And then we will make some summary of the finite element history and introduce the strain displacement relation. Following, we will introduce the theory of the stress and the deformation. And then is the stress-strain temperature relation. Finally, we will talk about the important part for the finite element analysis is that the computer answer may be wrong problem. Okay, this topic is very important. You can is that you can check your numerical result obtained from the finite element analysis is correct or not. So the lecture will introduce the subtopic, and all the subtopic are referenced by the Cook RD chapter 1. Now we will introduce the finite element method. In this slide, we will show you what is a finite element method. The finite element method is a numerical procedure for analyze the structure and the continuous. And this method can be applied when under this condition, when the problem is too complicated to be solved by the analytical solution. Analytical solution obtained from the journal paper or textbook. So because all the analytical approach and have so many assumption to simplify the problem, but the problem after simplify is too as compared with real condition are totally different sometimes. So for actual engineering application, this is not good by using classical analytical method. Therefore, so this is the reason why the finite element is so important for industry and engineering application. The problem in engineering, such as structural or stress analysis, heat conduction, or others, several others areas of the problem. And next, I will introduce the finite element procedure. The finite element procedure. After performing the finite element procedure, we will obtain many simultaneous algebraic equation at the same time. In other words, we will get a matrix form for this equation. But for the model have the many element at the node. It means the unknown values in this model, such as the displacement, is too many. So we can not solve by your hand directly because the matrix is too large. So we will use the computer to calculate the matrix. Once the matrix is solved, we can get the unknown value such as the displacement. Once we get the displacement, it means we can get the strength, right, for the structural analysis, and then we will get the stress by the Hooke's law. However, the error are decreased by processing more equation, and the result accurate enough for engineering purpose are obtainable at reasonable cost. Okay, and it means we can use the finer mesh to model the structure your concern, but it means the element becomes smaller and smaller, and the node number becomes many and many, right? In other words, the algebraic equation become more and more. So the matrix we need to solve become larger and larger. So the computer time will be longer, and we will spend more cost to solve the problem. So you need to get a balance between the calculate time and the accurate the solution. Now we will use the Chinese version to repeat again for the finite element procedure. 同学，我们在做有限单元法的模拟的时候，我们通常在步骤里面呢，最重要步骤我们有讲说是要解那个切割网格。切割网格呢，有个问题就是说，当我切割的element 的数目变多的时候，我应该这样讲，我切割网格的时候呢，基本上这些网格所产生的 element 跟节点呢，尤其是节点上面有未知的数，这些未知数可能是 displacement 或是 temperature。好，那这些东西呢，这些的未知的一个物理量呢，在一个 element 的里面呢，会形成一个 element 的 stiffness matrix， 还有一个unknown 的 value， 譬如刚才讲说 displacement 是 temperature， 那这些都是变成一个代数方程式。那经过 assembly 变成 global 的一个 stiffness matrix 的一个情况时候呢，就是这个 matrix 呢是代表整个modeling 的一个我们要求解的一个代数矩阵。代数矩阵，代数矩阵，方程式方程组方程组。那这时候解这个 unknown 的一个 displacement 或 temperature 的时候，这就是要同时解这个结构或是结构里面的这些我切割网格的这个节点的一个未知量，那未知数我就要把它求出来。那当然，一旦我的位移譬如说我使用位移，前面有介绍我所谓的位移法。把它求解完以后呢，我可以得到这些节点的位移。一旦节点位移知道以后呢，我就可以知道我的应变。应变知道以后，经过 Hooke's law 呢，我就可以知道我的应力值。这个节点上面的应力值。那当然，你切割的网格数越多的时候，代表 你所会产生的一个代数方程式呢就越多，也就是说你这个矩阵会越大。这矩阵越大的话，代表你计算时间就要花费的非常的久。那代表，那当然你的那个结果的一个精确度就还不错，对不对？因为你越切越细，但是你花的时间越久的话，花的时间越久，有时候我们在工程上面应用的话等不及，所以我们在做有限单元法的时候，你切一个网格，你必须要在结果的精确度还有计算时间上面取一个平衡。你计算时间越久的话，代表你切个网格数越多，好，切个网格数越多，你得到结果越精确。但是你如果切个网格数不足的话，你的答案可能会稍微不精确一点点，但是还是可以接受的话，好，那当然是可以工程上应用。所以各位同学去想一想哈，在工程应用上面呢，这会有一个 balance 的一个情况，出现哈，就是你自己要去拿捏怎么样去做适当的一个网格，好和计算时间。Next, we will move to the next slide. Next slide, we'll talk about the original or the finite element method. The finite element method is originally dated as a method of the stress analysis. So this approach is come from the structural analysis. So first, the finite element also used to analyze the problem such as heat transfer, food flow, electrical, and so many other fields. The application of the finite element procedure, such as the design of building, electrical motor, and the heat engine, ship, airframe, and spacecraft. So many industry and application and in life will use the method to calculate the structure or temperature or other concern analysis. So next, I will talk about who will use the finite element method and the software. Actually, the manufacturing companies and the large design office will like to use the finite element software. The companies and the design offices usually has one and more large finite element problems, such as the ANSYS and the Abacus and so on. But as you know that the software are expensive, and some company and the design office cannot have enough the money to buy this software. Oh, so they will like to use the stress free, as normally called free download. Okay, free download the software or online finite elements software, but who will use the online and the free cost the software, the smaller company, okay, to access to a large problem via a commercial computing center or use a smaller problem on a PC. Okay, it mean the software, the finite element software, may be expensive, but the commercial computing center such as 国家高速电脑中心 have this software. You can buy the computer time. For example, if the case you expect to run 1 week, okay, you can spend money to uh, to you can spend money to buy spend money to buy this the time to uh, to run your simulation at the computer center. Okay, this is more cheap when as compare you buy a copyright software directly. So some smaller company or the design office, if they do not have so many money, they will use the software by this way. 同学一般来说哈，有限单元法的软体哈，在制造的科技厂啊，或是大的那个设计的一个办公室呢，哈 ，design house 呢，它基本上会有至少一到多套的一个有限单元法的程式，譬如说 ANSYS 的一个商用软体，或者是 Abacus。但是呢，这些的软体呢，上次我们讲说是非常非常贵哈，尤其像 ANSYS 哈，现在基本上工业版的一个 license 一套就好几百万哈，300-400万。那基本上一般的小公司是负担不起的哈，只有像台积电或是联发科等很大的公司才有办法买断这些软体。那所以基本上小公司如果要使用这些软体的话，它有一个方式就是说，我们园区里面有一个国家高速电脑中心，那它会提供这些原版的那个像 ANSYS 或 Abacus 的软体，只要它那边有的话，你可以用它那边的硬碟哈应该说硬体资源、计算资源，跟它买时数，譬如说你的结构你的分析要在那边 run，要那边跑1个礼拜，你就要买1个礼拜的时数，好，这个详细的钱我不是很清楚哈，但是基本上会比这个买断一个软体便宜很多，但是有一个风险哈，就是如果你乱到一半呢，你的结果发散的这些时数还是要照算哦，因为使用者使用时间还是要照算哦，还是要照付费，所以通常哦，在实验室在学校来说，如果你的想要实验室有可能碰到的情况，就是说你 run 的时间非常的长，那你可能要先确认你的结果在能够收敛以后，再丢到这些国家高速电脑中心里面去计算，会比较保险，以免说 run 到最后又发散的，反而是这些买断的时间买断的钱还是要照样付费哈，就觉得有点怄了嘿，好是这样子 ，OK。If no problem, we will move the next slide. Next slide, we will talk about the basic the finite element concept. The first step is the discretization. 离散化 discretization. You can image it. You can image this the picture. This picture is it's a bar. It's a bar, horizontal bar. The one end of the bar is fixed. Another end is applied by a force P, actual force P. And the total length is L. The total length is LT. You can image the displacement U on the right of the bar, right? After applying the actual force. Okay? So, from the viewpoint of the classical approach, we need to write a differential equation for the bar. It means the displacement U is a function of x, and solve it to find U at the x is A L T at its location. Okay. This approach is can be obtained by a classical approach, but from the viewpoint of the finite element approach, the first you need to discretize the bar by modeling it as a series of the finite element. You can reference this figure. The bar is discretized as 4 element。这个 bar 呢，这个那个bar 呢，被离散化4个 element 哈，4个 element，and each element has a different cross-sectional area A。这个4个 element 呢都有不同的那个截面积 and the displacement U varies linearly with the x. Okay? And in location of the each element, delta is obtained from the equation. Delta equal to PL over AE. P is axial force. L is total length of the bar. A is the cross-section of the element. E is the Young's modulus and all the elastic modulus of the element, and then sum it. By this way, you can get the elongation of of each element. Okay, of the totally bar. Sorry. 同学，基本上如果你使用那个有限单元法的话，基本上你可以把它离散化。啊，以这个图来看的话，我们把这个 bar 呢离散化成4个 element。这个每个 element 呢，它有不同的一个 cross section 截面积 A 哈。那基本上它的截面那个每一个 element 的位移呢，是线性的，沿着随这个变数 x 至水平方向的一个位置而变化。那当然它的一个伸长量或是压缩量，这边是写 elongation delta 伸长量每个 element 的伸长量，它使用这个是材料力学里面的一个轴向方程式，对不对？delta 等于 A1 分之 PL， 这是由 Hooke's law 的一个一维方程式所推导出来的。那这样的话，你可以得到第一个 element、第二个 element、第三个 element、第四个 element 分别这个 delta， 也是 delta 1、delta 2、delta 3、delta 4。那把这个4个 delta 呢，把它加总，就是会得到一个 total 的一个 delta。这个 total 的 delta 呢，就是代表这个 bin 的一个这个 bar 的一个总位移量哈。那基本上是这个概念。那当然，如果离散化的 element 的数目越高的话，那你的那个怎么讲？你的结果呢会跟classical 的一个 approach 得到的结果呢是会越来越接近哈，是越来越接近的，到达一个很小的一个误差存在而已。As you know that in this figure we just give you an example have the four element in this bar, but you can discretize more element. For example, from four element increase to 10 or 20 element. Okay, but at this moment, the situation, you can get a more accurate the solution as compared with the classical as compared with the result obtained from the classical approach. So depend on how finer final mesh you create for the structural modeling. Okay, but at this moment you need to care about the calculated time. If no problem, we will move to the next slide. Okay, this slide just show you the basic finite element concept. As we talked about in the previous slide, the for this the example, the accuracy of the solution can be improved as more elements are used, and the finite element model a structure as an assemblage of the small part. It means the elements, and each element is a simply geometry, right? And we can approximate a complicated solution by a model that consists of the piecewise continuous simple solution. Okay, and the elements are called finite because we use numbers of the element, not infinite, to reduce them from the differential element used in calculus. Let us move to the next slide. The next slide just show you an example to expand the relation between the displacement and the strain and the stress caused by the pressure P as referenced by the this figure. This figure is a structure and a hole insert, and the hole is within this structure. One side is fixed, and the partial of the top surface are applied by a pressure P. And we give a coordinate system xy at the left bottom corner of the structure. And the finite element are modeled by the triangular or quadrilateral area or element. After modeling or by the finite element, elements, the finite element model are shown like this way. Okay, and the black dot called node or node point. Okay, where elements are connected to one another, and each node in this case has 2 degrees of freedom. In other words, x and y directional displacement. If we have n node, mean this model has 2n degree of freedom. And this model can generate algebraic equation describe the finite element model. And we use the algebraic equation to form a matrix and solve the unknown value of the matrix this equation by the matrix form to determine the degree of freedom. In this case, the degree of freedom means the x and the y directional displacement. And this is just show you an example that for the for considering the node 3. The node 3 have a displacement along the horizontal direction, mean the U3, okay? Mean the U3. And this just show you the directional displacement along the node 3 along the horizontal direction. However, the node 3 has another directional displacement along vertical direction. Okay, along, in other words, in the y direction. 同学，这个是说我们基本上给各位一个 case 如这个图所示。这个图呢是说有一个结构，这个结构有一个洞在这里面其中呢它的左侧呢是 fixed 的，那又在它的结构上半部上半的表面的一个部分的一个区域，我们给它施加一个 pressure 在那边。那当然，我们这个 model 呢是可以就是离散化用 mesh 的方式把它变成一个有限单元法的 model， 像这个图 B 所示。那图 B 呢，这边很多一个黑黑的一点一点，对不对？这个黑黑的一个一个点呢，我们称为节点 node or node point， 我称为节点或是 node or node point。这个节点呢，基本上呢，我所有的自由度呢，都是定义在这个节点上面。那注意一下，我们在 mesh 这件事情的时候，做 mesh 这件事的时候，我们要使用二维的一个 element，同时也要定义它的一个坐标位置。以这个例子来看的话，它坐标位置的原点是定义在这个节点的这个 model 的一个左下角的这个位置，那分别是 S、Y 的一个坐标系统。那 S 方向呢，定义有一个 U 的一个 U 就是 S 方向的一个位的自由度 U。那 Y 方向呢，也有一个 V 的一个 vertical 的一个 displacement 自由度 V。那如果一个节点上面它拥有两个自由度的话，分别是 S、Y 的一个 displacement 话，那所有在构成这个 model 的一个节点，总共如果有 n 个的节点的话，那它的自由度要乘以2，对不对？因为有一个节点上面有两个自由度，就有2n 个自由度。OK， 这个2n 个自由度呢，换句话说，就有这么多的一个未知数，未知数必须要求解。那每一个未知数都有一个代数方程式，代数方程式所描述。那这些代数方程式，我们可以用矩阵方式来表示，来解这个未知数，就像我们前面讲的一个位移法。那一旦解了这些利用高斯消去法解这个 unknown value 以后，一旦得到以后，我们就可以用这些已知的一个位移呢，去描述每一个节点上的一个对应的一个位的一个变化。如这个图三所示的话，这个是说我这个虚线的位置呢，是我给它一个假设，这个节点上呢受到一个水平的一个作用力 P3， 它对应的位移量就是 U3， 就是这样子而已。OK， This figure is follow the previous slide. Let us reference these figures again. From the figure A and the figure B, you can see the distribution pressure P has convert to concentration force A naught. Again, the pressure P in continuous structure become concentration force applied at these 3 nodes. Okay, and in addition, the element must be restricted in their deformation pattern. For example, let us reference the figures. C. Elements are allowed to have only such the deformation mode, as will keep the edge straight. A cursor element will neither overlap or separate. In other words, if the adjusted element occur, this situation, it means these two elements are separate or have a crack along this edge. So this is necessary to satisfy the compatible the situation from the viewpoint of mechanics。同学，基本上呢 ，Figure A 跟 Figure B 呢，是代表说在连体力学，在连体的一个结构里面呢，我们施加一个 pressure P 在这边，好，在这几个角落，在这个角落位置。那当我们转换成有限单元法的模型之后呢，这些 pressure 的 P 呢，会变成什么样子呢？基本上在有限单元法的模型里面呢，它会转换成集中力，集中力的方式呢，施加在对应的这个位置上面的一个节点上面。当然，你看这个箭头有长有短，这代表它的 apply 这个集中力的一个大小。那这个会根据 weighting 的一个方式去做这个调整，做这个调整。好，那基本上呢，另外一个必须要注意的是说，我的 element 之间呢，它会怎么做这个变形的一个联动呢？好，主要是会受到一个变形的一个 pattern 的这个图案，就是变形的样子的做影响。举例而言我们参考这个其中一个 element， 这个 element 呢，它有4个节点，1、2、3、4。这个4个节点呢，当受到这个 pressure P 作用以后呢，理论上来说，每个节点上面都有 S 方向跟 Y 方向的一个力量分量。那基本上在这个4个节点所组成的一个单一个 element 里面呢，如果我今天节点3呢，有一个位移有受到一个 P3 的一个力量分量作用的时候，各位可以想象它会怎么变形吗？它只会沿着这个水平方向做一个直线的一个比例的一个变形。有看到这个虚线吗？它保持一个水平的直线做变形的动作，那各位可以想象，这个2号跟3号这个节点的旁边这个 element， 它的变形会跟着怎么变形？会沿着这个虚线这条线跟着变形哦。好，那不会 overlap， 也不会 separate， 也不会 overlap， 也不会 separate。那如果是这个情况的话，是满足所谓的 compatible 的一个 condition， 也就是相容。相容性基本上就是说我的变形呢是连续而且是不会有那个数值上的一个错位的一个情形，这个才是会满足力学上的一个条件。Okay, let us move to the next slide. This slide just show you a basic behavior of an element, as shown in this figure. In this figure, we have the several element type that are possibly by considered in this figure. Okay, so in this figure, for example, we have 3 types of the element: triangular, rectangular, or high order rectangular element here. And we use the function phi to express any of several physical qualities such as displacement or temperature and so on. And when we use the finite element model to represent this model, this is the structure. It's typically yielding a piecewise a smooth phi. Within each element phi, within each element, phi is a smooth function, okay, represented by a simple polynomial. For example, in other words, we can define a function phi. The function phi is dependent on the location xy, okay? And the function phi is has the form of the simple polynomial. Okay, so by use the function phi, we can know the displacement or temperature variation within the one element。同学，基本上我们在讲这个开始讲这个element 的一个 behavior 的时候，各位同学可以看一下这张图哈。好，这张图呢并不是一个三维的一个结构图，它只是二维的表示。看一下它的坐标轴分别是 s、y 跟 phi。这个 phi 呢是我定义的一个 function， 好 function。那基本上这个 phi 呢，根据你分析的一个情况形式不同而有所不同。比如说你在分析结构的时候，这个 function phi 呢，它就是 displacement。在分析那个热传分析的时候，它有可能就是 temperature。好，所以它有很多可能想要看到的东西如这张图所列的这些可能的变数。那这个 function phi 呢，它基本上可以用 polynomial 一个 equation 去表示，好，简单的一个 polynomial 多项式来表示。那基本上这个 function phi 呢，对于每一个 element， 对于每一个 element， 它都有在每一个 element 它都是一个 smooth 的一个 function。好，当然 element 跟 element 之间它是一个 piecewise smooth 的一个 function。OK， 好，那这张图怎么看呢？这个呢，基本上呢，这个是SY 呢是坐标位置结构，这个还是考虑二维的问题是坐标位置。坐标位置在 SY 的时候，某一个 SY 的时候，它对应到一个 displacement。坐标轴在譬如说 S2、Y2 的时候，它对应到另外一个 displacement。好，以结构分析来看是这个样子所以基本上可以用这个方式，这个只是把它三维化来表示。那基本上各位可以看一下，这个图上面有三种不同的一个 element type， 分别是 triangular、rectangular 和 high order 的rectangular 的一个 element。那这个三角什么叫 high order 呢？基本上也就是说，除了空的之外，在边上也有节点这叫 high order 的一个 element。好，那根据你的 element 的 type 的不同，你的那个 share function 的 polynomial 的一个形式也会不同。I just said that depends on the difference of the element type, how to define the polynomial form will be different. Okay, because the detail will be explained later. Okay, let us move to the next slide. For example, when we consider the triangular element, please reference this figure again. We use the linear polynomial phi equal to a1 plus a2x plus a3y, and the coefficient a1, a2, a3 are constant. What is the variation S and Y? SY is the location of the element or node. Okay? Sorry for the node. For the four node quadrilateral element, we use the bilinear function. This is just one example. We have another definition for this function. 这是双线性的一个形式。Phi equal to a1 plus a2x plus a3y plus a4sy. Okay? It should be noted the 8th node quadrilateral has 8 a1 in its polynomial express. Okay? This is for a node. This equation just for node element. But for a-node element, the polynomial equation maybe is a parabolic surface. So by these two equations are interpolation of the function phi in terms of the position xy within an element, and we need to determine the ai in terms of the nodal value phi. OK， 同学基本上我们可以用这两个形式这个举例譬如三角形呢，我们用线性的一个多项式来表示 phi 等于 a1 加上 a2x 加上 a3y。那其中 phi 呢，基本上它就是刚才讲说，它可以表示成这个 element 里面的一个位移的变化。那位移的变化它是 function of sy， function of sy 对 s 而言，对 y 而言，它都是一个线性的一个方程式。那对于这个4个节点而言的一个 element 来说，那基本上我们使用的一个是双线性。什么叫双线性呢？如果你把 y 视为一个常数的话，对 x 而言，它是一个线性方程式。那如果你今天把这个同样的道理如果你今天把 s 呢视为一个常数的话，那对 y 来说，它也是对 y 的一个线性方程式的表达。好，那这种形式的话，通常我们后面会介绍会介绍这个情况。那对于另外一种四边形的一个 element， 它如果是从节点跟边上都有节点的话，从空的跟边上都有节点的话，那基本上这种话的这个 phi 的一个表示的情况，会变成一个抛物线的一个 surface， 并不是一个线性的一个 surface。线性的话就硬邦邦的这条线，那这个话就会比较有曲面的感觉。好，那注意一下，这边有个说明，就是说我的这个 phi 呢，通常我们称为 interpolation 的一个 of the function， 那它是跟位置相关位置 sy 相关那这些上面的这些系数呢，必须由节点来决定的那基本上我们后续的推导会知道说，其实 ai 呢，这每个系数呢，都是由这个节点上面的一个节点上的一个值来做 weighting 的一个动作。Okay, if no problem, we will move to the next slide. Okay, how to decide which element use? The answer is not simple. First, we review again the definition of the finite element method. The finite element method is a method of piecewise approximation in which the approximated function phi is formed by connected simple function, each defined over a small region. Here is the element, and the finite element is a region in space in which a function phi is interpolated from nodal value of phi on the boundary of the region in such a way that the inter-element continuity of the phi tend to be maintained in the assembly region. Okay, so the definition is very important. Combine this the concept and the previous slide. I believe you know the finite element, the basic concept of the finite element. And the following, I will list the steps of the finite element analysis. The first, we need to divide the structure of continuous into finite elements. Then formulate the properties of each element. It means we need to care about the condition that allow deformation or temperature, and then assemble an element to obtain the finite element model of the structure. This is from the viewpoint of the structural analysis. And then apply the norm loading. Okay. In stress analysis, we need to assign how the structure is supported. These two steps are, are concerned to the boundary condition and the loading, and then solve simultaneous linear algebraic equation to determine the nodal degree of freedom. In this step, we need to prepare a matrix form of this algebraic equation, and the unknown value usually are the nodal displacement. And finally, calculate element stress and strain from the nodal degree of freedom. Okay, so these 7 steps are the major procedure when we perform the finite element analysis.
Okay, this slide just show you some example application. In this example, is actually symmetry rocky nozzle. As shown in this figure, the left side is the detailed structure of the rocky nozzle, and the right side is the possible mesh model of this rocky nozzle. You can see that each element has a node at each the vertex, and the stress caused by the temperature gradient, and the internal pressure are deserved. So the temperature gradient is come from the heat transfer analysis and need to input to the structural analysis of the finite element. And we will apply the internal pressure around the inter surface of the rocking nozzle. So if you want to get the accuracy the result, you need to carefully handle the boundary condition and how to apply the loading based on your actually situation of the problem. So this is very important when you handle such the problem. Okay, in this the example is an arch dam. You can reference this figure. When you modeling the arch dam, we select 3 kinds of the element. The first is the quadrilateral and quadrilateral element, and the second is the triangular element, and the third is the single qubit element. And you can find that in each kind of the finite element modeling based on the element that we talk about are the are, are are different based on the location of the node. So when you can see the model, you can see the first model we use the quadrilateral element. The element is based on the isoperimetric the solid element, and based on the loading condition, the stress induced by the hydrostatics and the gravity loading. And when we consider the stress distribution for the arch dam, you need to consider the fluid structural interaction. This is very important, and when we need to consider the condition B and the condition C, the modeling. If you want to reduce the element number of the model, you can select condition B and C. But in common situation, we select element of the figure A。同学，基本上呢，我们会这个是一个针对水坝的一个模拟哈，模拟。那基本上这是一个1/2对称的一个有限单元法的 model。那各位也知道哈，就是说模拟那个建构这个有限单元法模型的时候，总共会有不同的，总共会有很多种，应该是说会有很多种的一个不同的一个 mesh 的一个方式。那 based on 你的那个选择的一个 element 的种类的不同，有所不同。那有一种呢叫做 isoparametric 的一个 solid element。那这种的 element 呢，意思是说它的节点呢，不只是在我的顶点上面，在我的边上也都会有哈，如这个图所示。如这个图所示，不只是在顶点上面也会有，在边上会有。那这种 element 的话，我们会在后续详述。那另外一个就是说，这几种modeling 呢，这个水坝的 modeling 呢，它的 stress 呢是来自于静水来压，也就是所谓的 hydrostatics 的一个的 loading， 还有重力的影响 gravity 的一个影响。那在做这种分析的时候呢，我们必须考虑它的一个流固耦合的一个交互作用的一个情形。那这个部分的话就，相对的来说就会比较复杂一点点哈。那第二种跟第三种呢，那另外一个需注意的是说，这张图上面也有提到第二种跟第三种的一个 modeling 的一个方法。那主要是在于差别说，我使用的一个 element 的一个种类的一个不同。那越右边的地方代表我使用的一个 element 的数目越少。你看，像最后一个 model， 它只使用一个 element， 那是这个 element 呢就有这么多的一个节点在上面。那各位可以想象，它就是一个高阶元素。所谓高阶元素，就是说除了顶点之外有 element， 有节点之外，在边边上面呢，在那个 element 的边上面呢，也都有所谓的节点在上面，只是它边上的节点不止一个，有那么多个在上边哦。好，这个是算是非常高阶的一个元素。通常我们不会使用那个 Figure C 的一个情况，我们都会使用这个 element 这个情况是属于这个Figure A 的这个图。Let us move to the next slide. Okay, in this example, we talk about the structural mechanics problem. In this case, is the plane and the bending element that's applied to an automobile frame. In this figure, just the final element model for this automobile frame. The detailed model are shown here. Used to find deformation, stress, natural frequency, and mode shape. So this final element is considered the vibration analysis of the structure. So we care about the deformation and the stress induced by the natural frequency. This is really important because the driver or people in the car need to feel comfortable, and we need to consider the structure, the stress of the car. So this is just give you an example like this way, and these three finite element contour from the left side to the right side are Berry-Housing model, deformed model, and the stress contour of the Berry-Housing. So this is this is easy to understand. This model is just the finite element model, and after analysis, we can get the deform model or the deform contour, and the right side of this figure just show you the stress contour. Sometimes we will show it like this way, just the contour, not by the color. 同学，这个呢是很典型的一个结构分析哈，我们是探讨这个汽车的一个车架哈的一个模型。那基本上在这个分析的时候呢，我们会考虑到它的一个振动分析哈，在自然频率下面是不是有可能造成所谓的stress 的突然变高啊，或变形变得很大等等。那这个分析就很典型的就是一个结构的力学分析哈。那下面这张图呢，从左到右呢，分别是这个Berry-Housing 的一个模型。那中间这个呢是经过分析以后所得到的一个模型的一个图案。注意哦，中间这张图跟左边这张图是不太一样啊，中间已经有变形了哈。那右边这张图呢是变形对应的一个 stress 的一个 contour， 就是所谓的应力分布。那通常有些会用等高线的方式来显示哈，他们会觉得这种方式会更清楚。那一般来说，我们当然可以用这个方式来表示，但是在 ANSYS 这种有限单元法的软体里面呢，我目前都是用所谓的颜色哈，从红到蓝色的方式来表现它的位移 stress 的一个变化。那当然是看个人的喜好了，来决定哈，这都没关系，只要看得懂就可以哈。Okay, if no problem, we will move to the next slide. Next slide just talk about the element characteristic matrix. When we talk about the element characteristic matrix, we call it as the stiffness matrix or conductivity matrix. When we perform the structural analysis, the matrix is the stiffness matrix. Okay, but when we perform the heat transfer analysis, we can call it as conductivity matrix based on the problem you prefer. In addition, we have three ways to derive an element characteristic matrix. The first is the direct method. When we use the direct method, it is limited to very simple element. Okay, based on the physical reasoning. 同学，这个我们有3种方式呢，来得到这个所谓的 element 的 characteristic 的 matrix， 就是 element 的特征矩阵。这 element 的特征矩阵呢 ，based on 你的使用的分析的element 属性不同而有所不同哦。如果我们今天是做结构分析的话，这个矩阵呢，就是称为所谓的进度矩阵，有些会称为柔度矩阵哈。如果你不是使用 based on 的未知数，好，在未知数如果说是未知数是位移的话，那这矩阵就进入矩阵。如果你的未知数今天是力量的话，节点力量的话，就称为柔度矩阵。那如果今天你分析的问题呢是所谓的热传分析问题的话，它就称为叫做热传导矩阵，好，热传导矩阵。那第一种方法是很简单，就所谓直接法哈。那当然我们在推导这个直接法的时候呢，我们使用 element 就要变得非常的简单。The second approach is the variational method. This method focuses on the when we use the variational method, you need to very care about the mathematical express because this kind of the approach usually stated by integral express. For example, potential energy 势能或位能。那基本上这种方法的话，通常都是用积分的方式来表达。The third way is the weighting residual method. The weighting residual method is the Chinese is the 权重法权重法。This approach is suitable to problems for which differential equations are known, but no variational statement is available, such as the guarantee method. In the lecture, we have one lecture focus on the introduction of the different weighting residual method. So the detail we will talk about later. 同学，第三种方法叫做权重法那基本上呢，这个方法其中最有名的叫做 guarantee 的一个 method。guarantee 的 method。那我们这个方法在稍后有一个章节会专门在探讨这个 weighting residual 的一个 method 这个方法很重要尤其里面的一个 guarantee 的 method。Okay, if no problem, we will move to the next slide. Okay, let us talk about the director method first. We give you an example of the elastic bar. The bar is regarding as an element, as shown here. Press a node at each end, node I and node J, and the only axial loading and the axial displacement. It means the bar just one element, and we have two nodes at each end. Call it node I and node J, and we also apply the axial force at each node, mean Fi and Fj. Based on the force equivalent, the Fj is equal to minus Fi. And we need to notice that the sign convention. The force and the displacement U are positive when directed toward the right. 同学，这个是一个element 那基本上左边跟一个 element， 那这个 bar 呢就是假设是有一个element 所组成的，那基本上左边是节点 I， 右边是节点 J， 在它这个 bar 的端点，那我们定义往右为正，不管是位移force 呢都是向右为正向右为正。The first, we need to consider the status, the equivalent, and based on the material is linear elasticity. And the first condition is that if we have nodal displacement Ui, it is larger than 0, and uj equal to 0. At this condition, we can get these two expressions of the fi and the fj. How to get these two equations? You can consider the Hooke's law. And find it based on the mechanics of the material. You can get these two equations. Another one, we consider ui equal to 0 and the uj is larger than 0. Please reference the figure B. You can get another two equations to express the fi and the fj. It should be noted that the simple L in this figure is bar length, and the simple E mean the elasticity modules, and we use A mean the cross-sectional area of the bar. Now we have get this four equation. The first two is come from the assumption. This is the condition. Mean we give the displacement at the point I. Another two equation is consider this condition of that we apply a displacement at node J。同学，我们考虑两种情况吼。第一种情况呢是说，我们如果施加一个一个位移量，在节点 I 的位置产生一个 Ui 的一个位移量，那 Uj 这时候我们保持零，就是说不动这个位移。那基本上在这种情况下面，经过建立平衡以后，我们可以得到这两个方程式。这个两个方程式呢，这是有材料力学上面那个一维的很容易推导的一个方程式哦。based on这个一维的 Hooke's law， 你就可以推导出这两个位移跟我的力量的一个关系。那同样的方法呢，我们考虑到这个 Figure B。那 Figure B 呢，这时候呢，我们给定一个位移量是在节点 J 的位置，节点位的位置，也就节点 J 给它一个大于0的一个位移量。那节点 I 的位移等于0。这时候你可以得到另外两个方程式，两个方程式分别表示节点 I 的力量跟节点 J 的力量。那这四个方程式呢，等一下会组成一个矩阵，矩阵在下一页。Let us move to the next slide. Now we consider the nodal force. The nodal force based on the superposition approach, we can get the final express of the Fi and the final express of the Fj. Okay? And then now we write the solution to a matrix form. And in the matrix form, we can get this equation. Okay? This is very important. This is very important. We have a remark here. A color of the K matrix. This is K matrix. The K matrix is here. The color of K matrix lists the nodal load that must be applied to the nodal degree of freedom in order to create the deformation state associated with unit value of the corresponding element of degree of freedom, while all other elements degree of freedom are 0. The second is that the stiff matrix is symmetry. Okay? And in this equation, the unknown value is the ui and the uj. 同学注意一下哈，那基本上我们在利用 superposition 方式呢，分别表示节点 I 跟节点 J 的一个最后的表示式。 那我们把它写成矩阵缝，就是像这样子的情况。注意，节点 i 跟节点 j 呢是未知量。那前面这个矩阵就是所谓的进度 element 的进度矩阵。那这个有一个 remark here， 就是说这个进度矩阵的每一个行，每一行值得叫做行，每一行呢是代表这个这个 force 呢，在这个节点位移上的一个在这个节点上面所对应到的改变位移的时候所对应的一个大小。譬如说改变节点譬如说我节点 i 给一个位移的时候，节点 j 不重的时候，我的 fi 的力量就是 a1 分之不 a1 over l。那如果今天只改变节点 j 的一个位移量，节点 i 是不动的时候呢，位移量是不动的时候，我们这时候可以知道这个节点 i 的一个反力呢，就是所谓的节点 i 的力量呢，就是 l 分之 a 负 a1 加一个符号。那同理，如果今天针对这个节点 j 而言，我们给定一个位移量 ui 的时候呢，它对应到的一个力量大小是 l 分之负 a1。那如果先是给定一个那个位移量是在节点 j 而不是在节点 i 的时候，也就是节点 i 是保持固定不动的时候，这时候 fi 的大小是等于 l 分之 a1 哈。Okay, if no problem, we will move to the next slide. Next slide just talk about another field application of the characteristic of the matrix for heat transfer or current conduction. Okay, the first is the Fourier heat conduction equation. Okay, I do not go through the detail. You can find it in the test and the reference book. The based on this equation, you can get the element matrix like this way. It should be net the unknown value in this matrix form is the temperature. Okay, Ti and Tj. If you consider only one element here, and the matrix here, the square matrix here is the heat flux. Is the conductivity matrix. Okay. If we consider another application for the electrical resistor, we can get such kind of the element matrix. It should be noted that we based on the Ohm's law. The current I is equal to the voltage difference over R. The R is the bar resistance. Okay, so we can do it like this way. Similarly, if no problem, we will move to the next slide. Okay, now we will talk about another loading condition. Please reference the figure A and the figure B. At this moment, the elastic bar undergoes no axial deformation. We apply the shear force and the momentum here. So based on the situation, we consider the elastic bar just have one element and two nodes at each end. So we apply the shear force and the momentum at each node. So in each element, we have the 4 degree of freedom. we use the simple W mean the lateral displacement, and the theta mean the rotation induced by the momentum. Okay? And now we consider the four situation. Please reference the figure C, figure D, and the figure E and the figure F. In figure C, we just apply the lateral displacement Wi. Other degree of freedom are constrained to be zero. So the deformation mode of the least bar can be imaged by the dashed line here. This is the first deformation mode. In figure D, we can in figure D we apply the momentum at the node I. So we can get a rotation theta here. Other degree of freedom are constrained to be zero similarly. Again, for node J, we perform similarly the way to get this kind and this kind deformation. Okay. It should be noted that we have in each figure. For example, in figure C, when we apply later displacement Wi, we can get the K22 and the K11 and the K21 and the K41 and the K31. The constant within the stiffness matrix the form because these four constants are related to the lateral displacement. Similarly, if we consider the rotation induced by the momentum, the matrix, the constant K22, K12, K42, and K32 are determined by this item. So I do not go through the detail for the figure E and the figure F, but similarly approach you can but if you use the similarly approach, you can get these two situation of the solution. So let us move to the next slide. So the stiff matrix based on the 4 degree of freedom, you can get the 4x4 stiffness matrix like this way. And we also have the nodal displacement vector. It's shown here. And the element stiff matrix equation is shown here. Just based on the previous case, we talk about that when we change the Fi, please reference the figure C. You can know that the F11, F21, and the F31 and the F41 are related to the Wi. If we change Fi, that let's induce the lateral displacement. If we apply the momentum I here, please reference figure BD. The matrix constant K12, K22, K32, and K42 are related to the momentum I and theta I. Similarly, if we give a lateral displacement Wj here, the constant of these four constant of the matrix of the stiff matrix are related to the Wj and Fj. Okay. Similarly, for the momentum J. 同学，这个就是说，我们前面一个很简单的一个轴向力的例子哈，我们衍生到这个例子。这个例子是说，我们考虑一个把遭受到这个侧向跟momentum 的力矩的作用，那基本上它会有一个节点上面有侧向变形跟旋转自由度旋转的角度，所以基本上以这个一个 element 来说，它就有4个未知数，因为节点上面有2个自由度，2个节点就有4个自由度。那我们前面有讲如果我们固定其他3个自由度不动，譬如说以这个 Figure C 来说的话，我们只给定一个侧向位移叫做 Wi， 那基本上这个进度矩阵进度矩阵跟它有关的系数就是 K11、K2、K11、K21、K3、K31、K41。那为什么会造成这个 Wi 呢？主要是因为我们也给它一个侧向的的 force Fi。那第二个 case 呢 ，Figure B 呢，第二个 case 呢，我们参考这个 Figure D 的这个情况。这时候我们在节点 I 给它一个 momentum Mi， 那跟 momentum Mi 相关的系数呢，就是均度矩阵的第2行。好 ，sorry， 第2行。那个第2行呢，这几个系数呢，就是由这个 Mi 所决定对应到的那个自由度呢，就是 sigma I。那以此类推，对于另外一个节点 J 的一个侧向 force 或是那个力矩作用时，它对应的进度矩阵呢，就是第3行跟第4行。OK， if no problem, we will move to the next slide.
Okay, based on the previous slide, we can find that for the direct method and consider the element stiffness equation. Is shown here. It should be noted that the K matrix is in terms of the element geometry and the elasticity modules composed of Young's modules, momentum of initials and momentum initials and the length. And you can find that just we talk about that the first column of the K matrix is determined by the activities only the first degree of freedom. For example, if we want to define the effect come from the Fi, the first column of the K matrix will be affected by the Fi, and based on we have the give a unit of the lateral displacement, and we want if in other in addition, if we want to find the second color of the K matrix, this constant in the K matrix can be determined by activating only the momentum Fi. Momentum Mi, the second of the degree of freedom. At this moment, the node I has a rotation of theta I. Okay, similar approach can be applied for the node J with only Fi and the momentum Mi. For example, if we consider the previous figure C, if the later displacement Wi equal to 1 and theta I equal to Wi equal to theta j equal to 0 are given in this condition, at this moment we can get the constant K11, K21, and K31 and K41 are shown here. Okay, it should be noticed that the simple E means the Young's module or elastic modules, and I is the momentum of inertials of the cross-sectional A. For figure C, is the cantilever beam form. So we can consider if W equal to 1 at node I, we can get this equation. And based on the force equivalent equal to 0, summary equivalent force equivalent, the theory, we can get is the equation. In addition, if we give a theta equal to 0 at node I, at this moment we can get this the equation. And based on the summation momentum equal to 0, we can get this equation. So at this moment, we solve this equation, we can get K11 equal to minus K31 and the K21 equal to K41. And the final solution are shown here separately. Okay, now I will talk about it by Chinese. 同学，这个直接法呢，基本上就是我们前面讲到的哈，就是说，如果我们今天是考虑到一个侧向的一个位移，还有一个 momentum 的作用，好，那这个 elastic beam 呢，它是一个的 element， 那基本上它可以写它的那个这个 element 的一个进度矩阵呢，可以写成这个形式，那基本上是4×4的一个矩阵，那后面对应的呢是它的侧向的一个位移，还有它本身这个节点的一个旋转的一个角度。那因为一个节点上面有侧向位移跟旋转的自由度，2个自由度，所以2个节点 I 跟节点 J 加起来就有4个自由度自由度。那对应到的话，当然是 force 跟作用在这个节点上的 force 跟 momentum 的一个影响。那诚如我们前面所介绍的，如果我们今天要决定这个矩阵里面的第一行的一个系数的话，基本上它跟哪些东西有影响呢？跟我的侧向给定一个侧向的一个 force 有关。只要我给定一个侧向 force， 其他的一个作用的外力，给它一个 0 的话，给它一个 0 的情况下面的话，我就可以决定第一行这个进度矩阵里面的第一行的所有的系数那举例而言，如果我考虑这个前面那一张投影片的 Figure C， 这个 Figure C 它是一个 cantilever 悬臂梁的一个形式。那 在这时候呢，我们给地节点 i 呢有一个单位的一个位移量，好，侧向位移量1。那其他的自由度给0的话，那我们就可以分别得到这个 k11 到 k21、k31、k41的值。好，那注意一下，这个 k 矩阵呢，基本上它由前面的就是我们有讲到，它是跟我的这个结构的一个杨氏系数，好，还有材料性质有关。I 就是 initial。就是那个moment initial of the cross-sectional area， 就是面积的一个惯性矩哈，面积惯性矩。L 是大写的 L 是全长，这跟我的 geometry 跟我材料系数有关系哈。好，那如果今天考虑到 Figure C 的情况下面的话，我刚才讲说是给这个侧向位移 Wi 给一个单位位移量1，那作用在节点 I， 那这时候是不是可以得到这个 equation 哈？各位可以去想一想这个 equation 怎么来的。那经过建立平衡，我就可以得到这个 equation。那另外呢，在这个节点上面的同一个节点 i 的上面呢，因为我们现在只是施加一个侧向位移，所对应到的是 Fi 的一个力量作用，但是没有 momentum 的作用，所以西塔是等于0。那等于0的情况下面呢，这个同学去想一想这个 equation 怎么来的。那在合力为0，合力矩为0，这一项是合力矩为0的时候呢，那我也可以得到这个 equation。那现在呢，同时解这两个 equation 以后呢，你就可以得到下面最后的一个答案，分别是 k11、k2、k11、k1、k21、k31、k41 会等于什么的值哈，都可以依序解出来。好，如果没有问题的话，那我们就换下一页哈。Let us move to the next slide. Now we will talk about assembly of the elements. Consider this figure. Figure A. The figure A is a cantilever beam. We have two different cross sections of the beam, and the cantilever beam, the fixed point is at the right hand of this beam, and the left hand have a axial force P apply here, and toward left direction is if we define the positive direction is the toward right direction, so the P is applied in the negative direction, right? So if we mesh the structure as the finite element model with the two elements, after modeling, the finite element model is shown here. Okay, the model is meshed by beam element, and we have two elements here. Now we need to consider how to assemble these two elements. Consider the element 1 and the element 2. The element 1 have two nodes. The two nodes is node 1 and node 2. Element 2 have two nodes. Node 2 and node 3. And node 2 is the common node below element 1 and element 2. And each node has 1 degree of freedom. That is S directional displacement. For example, node 1 has a degree of freedom U1. Node 2, U2. Node 3 has a degree of freedom along S directional displacement U3. Okay, and the element 1 length is L1. Element 2 length L2. For element 1, based on the previous slide, we can get the element stiffness matrix K1 is shown here. And for element 2, we can get the stiffness matrix for this element K2. The detail is shown here. Okay, these two has its own stiffness matrix, right? We call it as element stiffness matrix, 元素的进度矩阵。Now we will assemble these two, combine these two, become one global structural stiffness matrix. Okay? As you can expect, because we have 3 degrees of freedom, suppose the stiffness matrix of the global matrix is 3 by 3 matrix, right? First, we consider the element 1 only. Element U1, U2. U1, U2, not 1, not 2. So we have the we need to number the row and the color of the matrix first. This is lot 1, lot 2, lot 3. Color 1, color 2, color 3. For the element 1, the number is 1 and 2. It means the K-matrix of this element need to put it in the number I equal to 1 and I equal to 2. Okay? So we can put the element stiffness matrix here. Okay? And for the element 2 only, because the node number is node 2 and node 3, and the color and the row number of the matrix is I equal to 2, I equal to 3. Color I equal to 2, I equal to 3. So for element stiffness matrix of the element 2, need to put here. Okay. Based on the previous slide, we need to use the superposition method to assemble these two matrices, right? So let us move to the next slide. So finally, we can get the global stiffness matrix. Here we call it as the structural stiffness matrix here. Okay, but the matrix K shown by this equation is singular. Why? Because the structure is unsupported now and can undergo a rigid body translation. 同学，这时候是没有任何的束缚存在，没有任何的边界条件，所以它会有钢体运动。So how to resolve this issue? Because now we do not apply any boundary condition and loading now. So next step, we will apply the boundary condition. Based on this figure, you can image that at node 3, the displacement equal to 0. So we apply U3 equal to 0. It means the third row and the third color of this matrix can be deleted, right? And the matrix is reordered as 2 by 2 matrix now. And then we apply the actual force P at the node 1 in the negative direction. So F1 equal to minus P. So now the structural matrix is presented like this way. At this moment, the matrix is non-singular matrix. Solve U1 and U2 directly at the same time. So you can get the final result like this way. Okay, if no problem, we will move to the next slide. Okay, once we get the nodal displacement and we interested the stress and the strain of this bar. So now we will explain how to get the stress and the strain for element 1 and element 2 based on the structure with the cantilever beam, with the form of the cantilever beam. So So based on the Hooke's law, the sigma 1 equal to E1 epsilon. Sorry, this have some error here. E1 epsilon 1. The epsilon means the strength, right? So this one is the Hooke based on the Hooke's law. We can get the stress-strain relation. And what is the strength? Based on the definition is delta u. Delta u mean the displacement. So displacement mean the u1 u2 minus u1 over totals or minus sorry u2 minus u1 over the original length of the element. So finally you can get this result, okay? Because u2 and u1 we have get in the previous slide. Similarly, you can get the sigma 2 equal to E2 epsilon 2 equal to E2 U3 minus U2 over L2. So finally, we can get this result. Okay, let us check. The sigma 1 equal to P over A1. This is correct, right? Because actual force is P. Cross section is A1. So normal force is P over A1. Yes. For element 2, actual force is still P1, but so it's still P, and now cross section become A2. So you can get the sigma 2 as the normal force for the element. So by this way, you can check the stress values and get the strain and stress the magnitude. And now we need to notice that the symbol for element and the structural stiffness equation are this express is based on the element stiffness matrix, and this one is expressed based on the global structural stiffness。同学，这两个有什么差别呢？这个里面的小 k 呢是代表小 k 跟大 k 呢都是所谓的进度矩阵，但是小 k 跟大 k 的差别是小 k 呢是代表一个 element 的进度矩阵，那大 k 呢是代表这是整个结构的一个进度矩阵。所以小 k 我们通常这个 element 的一个那个 element 的 stiffness， 那大 k 呢我们称为 global 的 stiffness， 那这边是称为 structural 的 stiffness。好，要注意这大小写的差别哈。所以在这边的符号大写跟小写不能乱用哈。小写在代表是单一个 element， 大写呢是代表 assembly 完后的一个 stiffness matrix。And in addition, the displacement d vector and produce the loading vector r based on the static equilibrium. So you can get the equation here. R vector means the load applied to node by the deformation element, and the R vector load applied the node by the external source rather than by deformation element. Everyone should be take about this point. If no problem, next we will summary the final element history. In the beginning, the lattice and analogs for structural analysis. In this the problem, the continuous is replaced by a regular pattern of the elasticity bar, and the current the first proposed the final element method. He studied the Sandvent torsion problem by the principle of the stationary potential energy and the piecewise polynomial interpolation of the triangular subregion. And then, final element method has a major advance as the PC and the programming language are developed. The detail I am not go through the detail. And later the graph create the named finite element method. It was recognized as having a sound mathematical foundation. As the solution of the variational problem 变分的问题 by minimization of a functional Chinese mean 泛函的最小值泛函最小值。那稍后之后我们也会提到一些关于泛函的一些概念。And the latest larger general purpose FEM program are emerged, such as ANSYS, Nastran, Dyna, and so on, perform statics, dynamics, and heat transfer analysis. And then the PC and the software have the graphite development, and this point become intensive. Later, a extension of the general purpose program began to appear on PC. It should be noted that about the paper, the journal paper or conference paper of the FEM was published in 1961, only has 10 papers. In 1971, this number, but in 1986, wow, the total number become huge, right? Now I cannot count the number because everywhere has the final element and related the papers and the report. So this is a summary of the final element history. And next, if no problem, we will move the next slide. Okay, and now we will talk about the strain and the displacement relation. Consider this figure. Now we have the two lines, the line 0, 1 and then 0, 2. These two lines are normal to each other, and the plane shape at this condition is before loading. After loading, the line 0, 1 become 0 prime, 1 prime. 0, 2 line become 0 prime, 2 prime line. Okay, so how to calculate the displacement in the x directional and the y directional the increment? We need to consider the displacement u along x direction is function of xy. Similarly, the displacement along the y direction v is function xy also. So now we need to make assumption that the displacement increment such as u common x. What is the u common x? It means partial u partial x. Partial u partial x multiply dx are very small in comparison with the u and the v. So based on this assumption, we can get the epsilon x. Sorry, have some error here. Please reference your handout to correct this the simple. Epsilon x equal to L02 prime 0 prime minus L02 over L02. This is based on the definition, right? Finally, you can get this result, partial u partial x. Similar, you can get the epsilon y. Some error here. You need to correct based on your handout. Epsilon y equal to partial v partial y. Okay, so these two equations, based on these two equations, we can get the normal strength. Okay, epsilon x equal to partial u partial x. Epsilon y equal to partial v partial y. In addition, when we consider the shear strength, here we based on the engineering definition, not the shear strength, okay? Or shear strength or shear stress. So now we will account the change in a right angle. Please reference this figure again. What is the shear strength? Based on the definition, it means the change of the angle, right? Before, after loading. So, what is the change of the angle? It means beta 1 and the beta 2, because initials the two lines are normal to each other. After loading, the angle remains here. What is the change? Beta 1 and the beta 2, we need to sum these two angles. So gamma sy mean the engineering shear strength equal to beta 1 and the plus beta 2. It should be noted that we assume beta 1 almost equal to tangent beta 1. Beta 2 is almost equal to tangent beta 2. So finally, we can get this result. Gamma sy equal to partial u partial y plus partial v partial x. Okay? So for the 2D, the stress and the displacement relation, finally you can get this equation, but some errors here, or some error of the symbol here. This one is epsilon x. Epsilon x equal to partial u partial x. Epsilon y equal to partial v partial y. And the shear strength gamma xy is equal to partial u partial y plus partial v partial x. But moreover, when we consider three-dimensional strength and the displacement relation, we need to consider the variable z, right? And the displacement along z direction, w. So we get another three equation. Epsilon z is equal to partial w partial z, and the gamma yz is partial v partial z plus partial w partial y, and the gamma zx equal to partial u partial z plus partial w partial x. We combine these six equations and get the matrix form. This matrix form is for 2D case. This matrix form is for 3D case. Okay, it should be noticed here. Some error of the symbol need to correct. This is simple x. Epsilon x is epsilon s, epsilon y, epsilon z. Okay? If no problem, we will move to the next slide to talk about the plane beam, the special case. When we talk about the plane beam, the case, please reference this figure. The left side of the figure A, is the differential slide of the beam that lie along the x-axis. It means we consider a beam in the SZ plane. Okay, we just consider the very small increment ds along the x-directional beam along the directional along the x direction, and now we need to define the height, right? The total height of the beam is t, and the neutral axis is identical to the x axis. And we consider one point P here. The P has a distance z as the matrix with the point C. Okay? And based on the standard beam theory, the transverse, the shear deformation can be ignored. So all the deformation and the strain are expressed in terms of the lateral displacement W. Okay, the W, partial x, partial W, and the partial W over partial x is assumed to be small. If very small, it means that this point and this value should be identical to the tangent theta, right? And now reference to this figure B. When we want to get the axial displacement u, we need to make assumptions such as plane cross-section are assumed to remain plane and normal to the deformed axis of the beam after its bend. Okay, consider this figure. The The first, in the beginning, the increment of this beam is like this way, right? After it rotates with a theta W1 over W1x, W1x. W common as, this is not 1, W common as partial W partial x, the shear strength here, theta here, okay? And after it rotates, the final situation like this way, okay? Consider the same point, P, moving along negative direction of the x-axis. Why? Initials, the point P is here, but now it moved toward negative direction. How to calculate this distance after it's bent? Consider this angle first. This angle is normal, right? This line and this line, the angle is normal. So the W common x plus this angle should be a 90 degree, right? And consider these two lines. This angle is still normal, right? 90 degree. See, right? A 90 degree. So this angle should be equal to this angle. Okay? And this value, this length should be identical to this length, right? So if we consider the z direction, distance z here, we can calculate this the length. Okay, the length equal to z times t multiply w common x. But now, so the size, the magnitude is the same, but now we need to consider the direction. It's moved to the negative direction, so we need to have a minus sign here. Okay, so so we can get the final result, u equal to minus z times common partial w partial x。同学基本上各位可以看一下哈，这是一个beam的一个其中一个微小的部分。那各位可以想象有一个beam呢，就是躺在一个二维的一个beam在 SZ 的平面上面。我们考虑其中一个很小的一个片段，这个片段的长度只有 ds 一个长度。好，那基本上这个 total 的一个beam的一个厚度呢是 t。好 t， 那假设它的 c 呢是位于这个beam的一个中心轴的位置上面，我们现在考虑到中心轴上方一个 P 的位置，距离这个中心轴有一个 z 的一个距离，那基本上呢，我们在做这件事情的时候有很多假设譬如说我的common partial w partial s 是非常小的，也就是说它的剪应变量是非常小的。剪应变各位可以知道它是一个角度的变化率角度变化如果变常小的话，代表它基本上是等于 tangent 的 tangent 的那个theta 它的等于 tangent theta。 那基本上它有做几个假设，在推导的时候，我的中性轴cross section 呢，在 bending 完呢还是保持垂直哦，跟我的那个 S 轴还是保持垂直的变形轴是垂直的所以各位同学可以看一下这张图，这张图我一开始的角度的变化呢是 partial W partial X， 就是这个，这就是剪应变的值。那这个角呢，这个角是不是应该等于这个角加这个角度是不是90度？那各位可以看一下这个两条线段，那这个角度加这个角度是不是也是90度？所以这个角度是不是等于这个角度 ？OK， 这个角度是等于这个角度。那这个角度是什么？就是剪应变值，对不对？剪应变的大小，剪应变是大小是不是就是刚才讲的 partial W over partial X？ 那如果这边有一个长度是多少呢？长度也是 Z 的话，我这个长度 Z 乘上我的这个角度，这个长度乘上这个角度，不就是它的一个这个我现在画起来的这个三角形的应该移动的一个大小吗？这个大小是不是等于这个 P 点的一个大小？移动的大小，如果这个长度是 D 的话，力乘上这个角度，不就是它移动的一个距离？这是往上，但是对这个点是什么？往左边移动这个大小的距离，这个大小距离就是这个 Z 乘上 W common X。可是这时候是作用在哪个方向？是在负的方向上面，负 S 轴方向上面，所以我们加一个负号。Okay, if no problem, we will move to the next slide. Actually, if zone X, sorry, have some error here. If zone X equal to U comma X, so you can get this, and U is equal to this value, this equation, right? So combine these two, we can get this. If zone X equal to minus Z omega partial comma double X, right? W comma double X is mean the curvature of the beam. We have some notation here. Let us strength matrix sorry, we need to get the strength and the stress relation. So we will want to define this the equation here. It means the strength matrix is partial displacement matrix, right? And based on this this equation, we can get here partial S. Sorry, if zone S is equal to partial matrix times displacement W. The partial matrix equal to minus Z D square over ds square. In this case, this value are scalar 是存量一乘一的矩阵就是存量所以这个还蛮单纯就是最后呢，我们可以把这个omega 呢跟我的sorry 不是 omega 这个位移量 W 呢跟我的应变之间的关系能够找到它有一个这个关系负 d 平方 over ds 的一个运算的一个大小。Okay, if no problem, let us move to the next slide. Next slide to talk about the theory of the stress and the deformation. Actually, this part can be explained in detail in the elasticity theory. The elasticity theory states the condition that must be met by an exact solution. please consider this figure. When we talk about this, the first we need to consider the stress equivalent. Please reference the figure A. The figure A. The figure A is the unit of the stress. At this moment, we consider the body force of this material. For example, we have the differential force Fx multiply the equivalent volume. The equivalent volume dV mean dx dy, the area, time the thickness T. Okay, so this is the detail the equation. And the stress and the body force are function of the coordinate, right? Now we define the coordinate along the plane is the xy plane. So the sigma s comma s is the rate of the change of the sigma s with the respective to x. The sigma s comma s ds is the amount of the change of the x over the distance x. I think this is no problem for the student in the study mechanics. Okay. If no problem, we will move to the next slide. Okay. Next, we will consider the free body of diagram and express the force equivalent. So based on the summation Fx equal to 0， 也就是在 x 方向要保持静力平衡，合力要为0。So based on this concept, we can list this equation here. The detail I do not go through. If you do not have any problem, you can ask the classmate or me or assistant also. And similarly, a procedure is can achieved by the summation Fy equal to 0. So based on these two equation, finally we can get these two equivalent equation here. One is along the x direction, another is along the y direction here. It should be noted that in this equation we still consider the body force, Fx and Fy. But the effect of the body force usually are very small as compared with the loading effect. So in this condition, the Fs and Fy are 0. Okay, so it means these two equations can be further simplified. Okay, only these two items here for each equation. In addition, these two equations can be used if acceleration is present. For example, the x direction acceleration ax imply that the fx include in turn rho ax. Rho is the density, ax is the acceleration. Okay, so it means, for example, in x direction has the acceleration, the equation can be rewritten like this way: sigma s comma s plus tau xy, comma y plus fy equal to rho ax. Okay? If we do not consider the body force, this item can be ignored here. 同学，基本上这个方程式呢，就是静力平衡方程式哈，在材料力学，在那个弹性力学里面会谈到哈。那通常我们会把大 body force 能够忽略，那忽略的话，基本上不管在 x 方向或 y 方向呢，只剩下就是 sigma s common s 加上 tau sy common y 会等于0。那如果今天不是静力平衡，而是有加速度的情形的话，那就动力学的问题，对不对？那基本上后面这个 item 呢，就变成 rho ax，rho 是指那个物体的一个值，那个密度哈 ，ax 是它的一个加速度值，好，加速度对应的加速度，在 s 方向的一个加速度分量。那同样在 y 呢，也是这样的写法哈，只是这时候变成 ay， 在 y 方向的一个加速度分量。If no problem, we will move to the next slide. Now we will talk about the comparability. The comparability is related to the stress and the strain, and the comparability condition is that the displacement field is continuous and the single variable. It means we need to satisfy this equation. Sigma s comma double y plus sigma y comma double x equal to gamma xy comma sy. The comparability relation exists among the strain if a plane displacement field is compatible. Most of the finite element methods are based on displacement rather than stress, and the comparability equation is automatically satisfied as one may see by substituting this equation into it. For 2D, the strain and the displacement relation, some arrow here, arrow bar here, arrow here, then you need to correct by your handout. And epsilon s equal to ux, u common s, epsilon y equal to partial u partial y, and the gamma sy equal to partial u partial x partial y plus partial v over partial x. Now we will use Chinese. 同学这边讲这个 compatibility 呢，基本上是讲我的应力跟我的应变跟的之间的连续性的问题哦。只要满足这个，基本上只要满足这个那个力量跟位移跟应变的关系式以后呢，基本上你的这个 compatibility 的 condition 会自动的满足哦，并不需要再额外去做设定。那基本上这个 equation 呢，在弹性力学的时候会证明，或高等材料力学的时候会证明，说这个 equation 是正确的。只要满足这个 equation 呢，基本上就是满足 compatibility 的一个 condition。那基本上我们在很多的一个有限单元法里面呢，我们的现在未知量都是未知数都是 displacement 而不是 stress 哈。那大概是这样子。那下面是讲这个我的二维的一个应变跟位的关系。这边因为有这个投影片显示的那个符号错误，基本上这边就是 epsilon s， 这边是 epsilon y。epsilon h 就是 partial u partial x， 这边 epsilon y 是 partial v partial y。好，那这后面就是简应变哈。那这边用 partial 意思呢，基本上我们是为什么是 partial 呢？主要是现在 uv 基本上是 function of sy， 是跟我的坐标二维的坐标有关系，所以我是沿着 s 方向的一个位移量，当然是要对 s 方向去做偏微哈。同样在 y 方向是做 y 方向偏微。Okay, if no problem, we will move to the next slide. Next slide just talk about the boundary condition. Okay, how to describe the boundary condition is very important because if once you setting the wrong boundary condition, that is garbage in, garbage out, right? The result is not correct, shortly. So, give you an example like this way. Please reference the figure. This figure should be the cantilever beam, look like a cantilever beam. How to set the boundary condition for this the structure and the show in the show the show in this figure. First, we consider the left edge. The displacement boundary condition at this edge. Sorry, I need to talk about. We need to define the coordinate system first. We consider the 2D coordinate system as y, okay, plane, and the s in the x axis we have the u displacement here, and the v displacement along the y direction. If have any displacement occur. So now we again consider the left edge. It at s equal to 0, ux uy equal to 0, right? Because this edge is fixed. Consider top edge. How to set in the stress boundary condition? The left run here. Sigma y normal stress and the top shear stress at this edge is 0, right? But for the right run, we need to apply the pressure. Pressure is applied in the minus y direction. So we need to apply sigma y equal to minus p. And at this moment, we do not consider any shear stress here. So tau sy equal to 0. And next, we consider the right edge. How to consider the stress boundary condition? At this edge, tau s equal to tau, in this edge, this is stress-free, right? So the sigma s equal to tau sy equal to 0. And how about the curved lower edge? We do not have any surface tension here. Surface tension, it should be noticed the unit of it. The unit is the stress. So at this edge, phi s equal to phi y equal to 0. Phi s, phi y mean the component of the surface stress here. If no problem, let us move to the next slide. Now we consider the boundary condition again. This slide just show you how to get the equivalent force equivalent equation from the boundary. Consider this figure. Consider this figure. This figure is the stress unit close to the boundary, and in this figure we have two surface tension component, phi s and phi y. Okay, the tension are s and the y direction of force increment. It should be noticed that their unit is stress, not force. It should be noted that the phi s and the phi y tension component, their units are stress, not force. So the stress are s and the y direction of force increment. Divide this by the boundary area increment dA on which they act. So the dA L increment is equal to thickness T multiply surface length ds. Okay, so based on the this is the relation, we can introduce the equivalent of the x and the y directional force, can get these two equations. Consider this figure again. We expand the detail for the first equation. Surface x, surface tension x, phi x, time multiply Tx, Tdx is dA. So this item become force. Okay, this one equal to this item in the negative direction, sigma x time dA. dA is equal to T multiply dy plus this item tau sy time this area. This area is dx time t. So we can get the first equation. Similar, we can another equation along y direction. For example, phi y here, surface tension in y direction. Time dA is Tds equal to tau tsy here, T dy plus sigma y here, time dds dtx. So we can get the second equation based on the force equivalent. And then delete t in each item and then introduce the direction of cosine dy over ds equal to L, ds over ds equal to m. We define the new item L and m is the direction of cosine. Finally, we can get these two equations. Okay, if no problem, we will move to the next slide. In the previous slide, when we talk about the surface tension, it's based on the 2D condition, but we expand to the 3D case. The surface tension equation have additional equation here. Okay, so totally for 3D case, we have 3 surface tension equation and 3 equivalent equation here. And consider this equation and the linear elastic body. If the stress or displacement field satisfy one equivalent equation, B compatibility equation, this item should be automatically satisfied. And 3, the boundary condition. These equations are belong equivalent and the boundary condition equation, right? So based on this the formula equation, we can find a unit and the exact solution for our concerned problem. On the other hand, for the finite element methods, we need to choose the suitable displacement field and also provide the compatibility between the elements and the satisfy displacement boundary condition. Therefore, the exact solution is achieved in the limit of an infinitely refined mesh. Okay, I think this is very easily to understand. So I will move to the next slide. The next slide just talk about some error of the simple here. In general, the stress vector here we have 3 normal stress and 3 shear strain here. For the strain vector, this is strain epsilon equal to 3 the strain vector have 3 normal strain vector item and 3 shear strain item. The first 3 is the epsilon s, epsilon y, epsilon z. Please reference your handout, okay? And for the isothermal stress strain relation, we can get this item. Sorry, this is the epsilon of simple. Simple epsilon equal to compressed Chinese mean 柔度矩阵 compressed stiffness all can be expressed by another form sigma vector equal to stiffness matrix times epsilon vector. Okay, epsilon vector. Okay, if matrix mean the stiffness matrix, inverse the stiffness matrix become complement matrix 柔度矩阵，一个是进度矩阵，另外一个叫做柔度矩阵。From an isotropic case， 意向性结构意向性的结构。These two matrices each has 21 independence coefficient. Okay, the detail I will show you later, but all the detail should be explain the detail in the elasticity course. Okay. Isotropic material. What is the isotropic material? An isotropic material that stiffness value is mutually normal direction. Okay, and this direction are called principal direction. If x, y, z are the principal direction, it means the normal stress sigma s, sigma y, sigma z are independent of the shear strain gamma sy, gamma yz, and gamma ds. At this moment, the stiffness matrix E has 9 independent coefficients from 21 reduce 9 coefficient. Okay. Because this following several slides will be Chinese, because the detail I think some students of you can be reference to the textbook of the elasticity if you are interested. But I will summarize the material properties for this item. Now I will use Chinese to explain the several slides. 同学，基本上我们这边讲一下这个应力应变的关系和温度的一个关系式哈。那因为这边是中文的一个部分，所以我用中文讲解。那这一页呢是一般的 case 哈，考虑一个连续体里面的某一个点所切出来的一个体积元素。那这就是所谓的应力单元哈。这个应力单元如这个图所示。那分别用我们前面用 SY 力来坐标，那分别在代表是它3个方向的一个坐标轴，对不对？那我们这边用那个数字1、2、3，分别代表是在 S 方向、Y 方向、D 方向的一个轴，好，正交轴。所以基本上这边 sigma SS 我就变 sigma 1， 同理 sigma 2、sigma 3呢，分别代表 sigma YY、sigma ZZ。OK， 那基本上剪切应力呢，我刚才讲说用数字1代表 S， 数字2代表 Y， 数字3代表Z， 所以基本上 tau for example tau sz 不 sorry tau yz 就是等于 tau 23，注意一下 tau yz 就等于 tau 23。那因为从我们材料力学可以知道，对一个应力单元而言，如果它可利用那个力矩拼的这个方式呢，可以证明 tau ij 等于 tau ji 具有对称性。所以基本上 tau 23就等于 tau 32等于4，我们用另外一个符号来命名它第4符号是来命名这两个 item， 用这两个 item 来用这两个 item 用 tau 4来取代。那同样的 tau 13等于 tau 31等于 tau 5，tau 12等于 tau 21等于 tau 6。OK， 那这是在应力的部分的处理。那同样的它这些应力的 item 所对应的正交应变呢，或者是剪切应变呢，基本 normal strain 或是 shear strain 呢，基本上我们用伽马的符号来表示。那刚才讲说 tau 23，我就用 tau 4。那伽马23，我当然就用 tau 伽马4来表示那伽马13就等于伽马6，伽马5，伽马12就用伽马6来表示。那根据 generalized Hooke's law 转移的胡克定律，你看应力或是应变呢都有6个 item， 所以基本上它就是6×6的一个矩阵的进度矩阵就出现了。好，那6×6的进度矩阵代表说有6×6等于36个系数必须要决定必须要决定。好，这个是 generalized 和 Hooke's law。好，考虑3种方向。那这个进度矩阵里面有36个常数必须要决定那这个是基本上是一个4阶矩阵的 IJKL。好，那如果说这个 detail 的话，可以去参考这个弹性力学的一个课程。那 for 这个 anisotropic 的 case 呢，它基本上有一个条件，就是 Cij 会等于 Cji。好，这个进度里面的 Cij 等于 Cji。如果满足这个条件的话，这个进度矩阵呢的这个进度矩面的36个系数呢，就变成21个独立的一个 coefficient。那如果进一步的化简成 isotropic 的 case 的话，那也就是说材料对力轴平面是对称的。好，举例而言对称于力等于0的这个平面，力等于平面的话，代表 s prime 是等于 s，y prime 是等于 y， 力 prime 是等于负力，对啊，对力轴对称嘛。好，所以力 prime 会等于负力，那所以会得到衍生这个以下6个等式。好，那同理，其他的方向也可以这样做的话，那 for isotropic case 就可以简化成9个系数。如这个图示，你看1、2、3、4、5、6、7、8、9，这边下面3个跟上面3个是一样based on an isotropic 的 case。这也就是为免我们前面2页有谈到说 for isotropic case 的话，基本上可以进一步简化成9个系数的原因。And next, we will consider the isotropic the condition. In this, such kind of material has no preferred direction, so the material properties are expressed as a combination of two of the following, such as Young's modulus E, Poisson ratio mu, and the shear modulus G. In its upper triangle of the matrix E, the matrix E has 12 zero coefficient and 9 non-zero coefficient as shown here. Okay. And at this the matrix we can get the E11, E12, but E22, E33 equal to E minus Poisson ratio multiplied C. And these 3 items equal to Poisson ratio multiplied C. And the E44, E55, E66 equal to G. It should be noticed that the C is equal to E minus E over this item, and the G is equal to Young's modulus over 2 multiply 1 plus mu, okay, inside. So finally, we can get this form and replace these two items here into this matrix. We can get the final matrix for the isotropic materials. Okay, if no problem, now we will consider some special case for the Planck's chain or Planck's trace. We consider the Planck's chain condition. What is the Planck's chain condition? It means the out of plane the displacement equal to 0. Okay, so it means, in other words, the Planck's chain. The strain in out of plane direction should be 0, including the normal strain, shear strain related to lead direction should be 0. So based on this concept for isotropic and isothermal stress and strain relation, the matrix form can be expressed like this way. Okay, sorry, some simple error here. This one should be epsilon s. This one should be epsilon y. In this item, in this equation, we cannot find the sigma z, right? But not mean the sigma z is 0. The stress sigma z usually is not 0, and we can obtain the sigma z from this equation. Okay. If no problem, we will move to the next slide. Next slide just talk about the Planck's chain condition. The Planck's chain condition, in other words, the out of plane stress should be 0, including the sigma z and the tau yz and the tau sz. And from the physical, the condition, it means the loading only in its own plane and without z directional restraint. 同学在那个平面应力的情况哈，基本上就是说力方向的应力是相关的应力的 component 呢是等于0的，而且在这个情况下面呢，所有的施加的那个力量哈都是在这个同一个平面，不会出现在 out plane 的方向上面哈，这个情况就叫 Planck's chain. So for consider the isotropic and isothermal stress strain relation, the equation can be expressed like this way. It should be noticed the detail. For example, E over G equal to 2 multiply E plus V, and the square matrix including their scalar multiplanar E over E minus Poisson ratio square, and so on. Okay. For the complanar, the matrix and the stiffness matrix. 同学这边它是用矩阵的方式来表示。那值得注意的是说，它前面有一个乘上一个存量的一个系数。那 for 这个楼度矩阵来看的话，它是乘上1分之1，1分之1。那 for 进度矩阵的话是1减 μ 平方分之1。Okay, it should be noted that we still have error, simple error here. This item should be epsilon s. This item should be epsilon y. If no problem, we will move to the next slide. Now we consider this condition of the beam bending. First, we consider the beam suffer an uniaxial stress. Sigma x equal to Young's modulus multiplied epsilon x. And from the previous slide, we have demonstrated that the epsilon s shall be equal to minus z displacement w common double x. Combine these two, we can get the stress, get the relation between the stress and the displacement. Okay. Now we want to find the bending moment n. So based on the fundamental definition, the n shall be equal to sigma s multiplied dA. Sigma s dA is the force, right? Force multiplied z become momentum. So integral from the minus t over 2 to positive t over 2 is mean the total thickness of the beam is t. Finish this integral, we can get this item. What is the integral for this item? This item is the momentum of the inertia. We use the I to replace the integral. So finally, we can get this equation. Momentum is equal to minus EI W common double X. A formula the express from the elementary mechanics of the material can be obtained. And it is the form of the sigma vector equal to E matrix multiply the strength vector. Let's apply to beam bending, and it's called a load displacement relation. Okay, I think this slide is very simple. So I will move to the next slide. Okay, now we will talk about initial stress and the strain and the thermal effect. This term, initial stress, means a stress present before deformation. It means initial have the strain within the structure. And this item should be allowed, which mean, in other words, it also means the residual stress. So by the equation of the formula, this equation can be expressed like this way: sigma stress equal to elastic matrix time multiply the total strain minus initial strain. Sorry, have some error, simple error here. Please reference your handout. This item means the total strain minus the initial strain, because the external force will induce the elastic strain directly, linearly, if the material is the linear material. So we need to minus the initial strain first, and this item contributes the elastic stress, and this item is the initial strain. So some elastic item and the initial stress item, we can get the final the stress here. 同学，这个是指是说，如果我们今天有讨论到初始应力initial stress 的话，初始应力有些人会翻成叫做 residual stress， 就残留应力。那基本上残留应力或是初始应力所 对应到的时圈的量，好，是时圈的量，我们用 epsilon 0来表示。那基本上这个我们要怎么表示这个方程式呢？就是说，如果我今天有一个含有初始应变的一个那个受力的话，我应该这时候所得到的最后的一个应变量叫做 epsilon，要先减掉什么？减掉初始应变量。这时候减掉这个以后呢，这时候的应变量代表是后来外力作用下面所得到的一个应变量，对不对？所以它基本上会跟这个elastic modulus 呢乘上一个线性比乘上一个线性比例的关系，得到这个最后的 stress。好，这时候的一个 stress 的值。好，这个时候是 stress 值。那这个 item 呢是来自于弹性的变化的一个情形。弹性应力应变变化情形。那这时候，但是最后还是要把这个初始应变的一个 initial stress 把它加起来以后，才是最后的一个 stress 值。我再讲一次哦，这个 item 呢，我们考虑是在受到外力作用的时候所产生的应力，但是所以基本上最后的应变值当然要先扣掉初始应变值。那这时候的弹性应变值乘上我的杨氏系数，就是我这时候对应的 stress 的大小。那这个部分呢 ，contribution 呢是来自于这个外力作用所对应到的一个 stress。那再加上初始应力以后，才会得到最后的一个应力值哈。And for free expansion of an isotropic material with the principal axis as YZ produce the initial strain. So the thermal strain or initial strain is equal to alpha T. Alpha subindex as YZ means the coefficient of thermal expansion along S and Y and Z direction. Okay, so you can get this equation. But for spatial phase and isotropic condition, you can get this result. I do not go through the detail for this equation. And then for the special case in plane stress condition, the initial strain can express initial strain epsilon 0 can express like this way, and the corresponding stress is shown here. In addition, for plane strain condition, epsilon 0 initial strain is shown here, and the corresponding stress is shown here. Okay. By definition, alpha is equal to partial epsilon partial t. This equation should be workable when the deformation is unconstrained. when the only alpha is independent of the t. And at this moment, the epsilon equal to alpha t。同学，这个呢，基本上 epsilon 等于 alpha t 呢，在什么时候才会成立呢？在这个alpha 呢是跟那个温度无关的情况下面，我们可以直接这样做哦。那否则的话，我们必须用下面这两个公式来求得对应的这个 initial 的一个 strain，initial strain epsilon， 还有这时候的平均的一个coefficient。average 的一个 CTE. If no problem, we will move to this slide. This slide just show you some remark. The first, Poisson ratio V is a little affected by temperature. The modulus E is affected more. For strainless steel, Young's elastic modulus decrease about 20% as temperature rise from 0 degree of C to 450 degrees C. Second, the elasticity properties are almost independent of the stress. Okay, this is very important. The remark. The third, the CT alpha is insensitive to stress but may vary with the temperature. So we need to care about the Young's molecules and the CT characteristic of our concerned material when we want to input such the material model in the finite element analysis. Okay, let us move to this topic. The topic is warning computed answer may be wrong. When we perform the finite element analysis, we may overlook or misjudge important aspects of physical behavior. There may be an error in the computer problem. Some computational path has never before been exercised or checked. 同学，我们在做这个分析的时候，有时候我们也会犯错哈，尤其当你对这个物理行为不懂，或是说这个分析的操作的一个路径或步骤不熟，那常常就会做一个误判的一个行为，导致这个结果错误哈。Far more likely cause of incorrect result are user error. For example, using in approximate problem, supplying an suitable program with the wrong data. Okay. The third, a poor match and the unsuitable element type and the wrong BC will introduce will result to the wrong error. Okay, and the finite element method is a powerful tool, but not the best analytical tool for every problem. Sometimes need to validation from actual test. Okay. In addition to finite element method, other numerical methods such as finite difference method, boundary element method can be used for spatial condition of the problem. Okay, I think this slide is very important because the powerful computer program cannot be used without checking. Their result cannot be trusted if user have no knowledge for their internal working or little understanding of the physical theory on which they are based. An error caused by misunderstanding or oversight is not correctable by match refinement or by use a more powerful computer. 同学，这一页是非常重要的我们即使就有更好的一个更强大的一个电脑的一个软体，譬如说 ANSYS 如果你没有任何的训练，或没有任何的一个验证的动作，那基本上我们这样做出来的结果通常都不会被相信那另外一个就是说，在使用 ANSYS 或是有限单元法的模拟的时候，基本上操作者使用者呢必须有强大的一个基础知识譬如说你要对材料力学对热传相关的知识要非常的精熟，而且也就是说对他们物理行为就这些产生的一些现象都要很清楚，才能做最好的一个模型的判断，模型的一个施加，还有边界条件施加。那如果你都没有这些知识，而只是一味的去 做这个 match refine match 哈 match refinement， 就是说你只是把这个网格数哈，觉得说啊，就是越切越多就会得到越好的答案，这是错的哈，这是错的，因为你的边界条件跟你 model 一旦都是错的话，你再怎么把这个 match 切得更细、更小，得到的答案都不会是对的哈。好，所以这个是非常重要的概念。当你使用这个有限单元法的软体或是分析的时候呢，你自己的基本的基础呢一定要打好，才能做这些分析。不然的话，你只是操作者，并不是分析者哈。我再讲一次，如果你只是你没有这个强大的一个基础知识的话，相关基础知识的话，你在学这个 ANSYS， 你最多就只是一个操作者，并不是一个很有经验的一个分析者哈。OK，this lecture of the is finished. So we will move to the next chapter in the future. Okay. Thank you.